Hello and welcome to the second of the lectures in this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered through the NPTEL platform. In today's lecture, we will look at how the need arose for fuzzy sets. The need for fuzzy sets can be traced back to both theory and their utility in practical applications. Allow me to give you a theoretical perspective of how the need arose for fuzzy sets. If we were to ask what is a set, perhaps the first answer that we would get is that it's a collection of objects. This definition is not far from what we have in mind of a set. For instance, if you list out the elements of X like this, yes, it's a collection of numbers and it could be called a set. However, when we think of this collection of numbers and call it Y, we do not call it as set Y, it is merely a collection of some numbers. This is because the element 9 repeats itself. One might ask, is there an issue? Well, some properties of a set that we would like it to have may not be possible to be defined uniquely. For instance, we may not be able to define the cardinality of a set if we allowed repetition of elements. Hence, the definition itself was refined as a collection of unique objects. Now, consider the set S, which is the set of all possible sets in the universe. Now, the question immediately arises, does S belong to itself? Now, towards avoiding such paradoxical questions, the definition was further refined as a collection of unique and well-defined objects. Now, to be able to decide on the belongingness of an element to a set is very essential. For instance, if you are given this set X, we can ask the question, does 3 belong to X or not? We will get a unique answer. Once we are able to answer this question at the level of an element, we could also do this on a collection of elements. So is Y a subset of X? Yes, that is also answerable. Now, based on this, we could also create properties of sets. For instance, if we know that X is a proper subset of another set U, then we could easily pick all those elements which belong to U but not in X. This is what we call the complement of X. And the interesting property between X and X complement are these. Together, they form the entire U and they are non-overlapping. Let us look at some qualities of an element of a set vis-a-vis itself. Allow me to present some scenarios. Let Q denote the set of all rational numbers. So the Q complement are those numbers which are not rational, what we call as irrational numbers. It is clear that the union of these two gives us the entire real line. Now, if you were to ask this question, does root 2 belong to Q? Of course, we know the answer. Root 2 is irrational, so it will not belong to Q. However, if you ask this question, does root 2 power root 2 belong to the set of irrational numbers? Well, of course, there exists a clear answer because it has to either belong to Q or Q complement. But for the moment, if we do not know the answer, then we are not in a position to give a clear answer to this. Now, if you look at this scenario, the set itself is very well defined, but what we do not know is the quality of an element, whether it is a rational or an irrational. Now, consider this picture, which is a collage of smaller pictures. Can we call this a collection of images? Is it a collection of unique images? Yes, perhaps, because the objects in the foreground, they appear distinct. So is this a set? Yes, but set of what? Perhaps we could say this is a set of birds. Now, if we agree to this, consider this image. Of course, immediately we recognize there's a penguin in it. But the question is, if we were to ask, does this penguin belong to the set of birds? Now, this is an often debated question. If you think of a bird, what characterizes or defines the quality of being a bird. Is it its morphological feature of having wings, or it's its essential quality to be able to fly? If we redefine this set as set of all animals with wings, then perhaps penguin will belong to this set. Thus here, the set originally was not well characterized, but it is redefinable. And once it is redefined, then the belongingness of another element, in this case that of penguin, to the set can be discussed and answered. Let's look at this famous paradox which you may have heard. So in a village there is a lone male barber. Let M denote the set of all the men in a village. S is a set of men in the village who shave themselves, and B is a set of all men in the village who are shaven by the barber. So clearly M is made up of the union of the sets S and B. In other words, you can look at B as the complement of S, and in that sense B intersection S should be empty. That means B and S should not overlap. However, if you ask the question, the barber, where does he belong? Does he belong to the set B or to the set S? You see that we actually fall into a very paradoxical situation. It appears that the barber probably belongs to both B and S. So now it has questioned the wisdom of one particular property, of insisting on this property, which is X intersection X complement. Should it really be empty? Of course, note that we have made two important assumptions, that all men in this village are clean shaven and the barber himself is from this village. Now, so far we may have seen that the properties of a set which we thought were inviolable, in some situations perhaps there is a need, there is a cause for relaxation. Allow me to present to you another example. Consider this table in which you have a few names, the ages of the corresponding people and their occupation. I have chosen only the occupation to be the student or professor. Now, given this data, we can ask some questions. So if I were to ask you to pick up the set T of all teenagers, I think it is easy to do. All you will do is pick all those people whose ages fall between 13 and 19. So in this particular list that we have, these are the teenagers that we have. Now we'll slightly change the question and ask, instead of picking the set of all teenagers, let us ask ourselves to pick the set of all young people. Now, who is young? Let us for a moment assume that all those whose ages have not touched 35 are young. So we put a hard threshold here. So strictly less than the age, strictly less than 35, we would call them young for the moment. So if you were to apply this criterion, then these are the people who could be called young. But notice that there are two people here, Meena and Gabriella, who are 33 years of age and are considered as young people. But there are two other people, Simon and Fatima, who are 35 years of age and they are not considered young anymore. Okay, let's redefine this set a little further. Instead of asking for the set of all young people, let's ask for the set of all young students. Clearly, Gabriella would lose it out because she is a professor, not a student anymore. But what is interesting is that even Meena would not be considered a young student in the natural sense of people who join school or college. Of course, it is contextual. We'll come to that in a later lecture. So, the very age of 33, which allowed Meena and Gabriella to be called young in the sense of young persons, they do not allow them to be called young students. Now, let's refine this or modify this a little further. Consider the set of all young professors. Obviously, many of them would lose out because they are students. Who should be considered a young professor? Let's say somebody who is 40 or below 40 of years of age, and a professor is considered a young professor. In that sense, these are the people whom you would call as young professor, those whose ages are marked in blue. But there is also one person, Bharat, who is just 41 years of age, who is not considered a young professor, whereas Shanti, who is 40 years of age, is considered a young professor. You see that to be able to put a threshold, a hard cutoff, and distinguishing people is becoming little unwieldy here. You should also note here that all the details of the elements which are necessary for us are known. However, what we are not able to decide on is who is a young person, who is a young professor, and who is a young student. So it is the character of the set that we are not able to clearly define. Is it redefinable? In fact, the question is about, is it definable at all or not? Let's look at this picture. So if I were to ask, what does it consist of? Once again, if you say that it's a set of blue balls, it consists of blue balls, yes, we wouldn't be far away from the truth. So let's say that it is a set of blue balls. Now the question is, I have another ball here. Now ask the question, does this ball at the right bottom corner belong to this set of blue balls? Now if you take a moment, part of you wants to say yes, part of you wants to say no. Because you're asking the question, how blue should something be to be called blue? Because blue itself is a concept. We talk about darkness, we talk about pitch darkness. So it is a concept. So if you were to ask, what is a fuzzy set? Perhaps one of the best ways to explain it is, it's a mathematical construct which captures a concept. For instance, consider the sets that we have discussed so far. If X is a set of teenagers, it's easy to discuss whether somebody belongs to the set or not. But the moment you relax and call it a set of young people, then we know that the concept young applies differently. It is varying, it is subjective, it is contextual. Similarly, when we talk about set of blue balls, blue becomes a concept. If E is just the epsilon neighborhood around 0, the moment you fix epsilon, then we are in a position to say whether an element belongs to the set or not. However, if you modify this, relax and say that let E tilde represent all those points that are close to 0, then this closeness, this proximity, it's a concept. It's contextual and subjective. So far, we have seen the need for generalizing classical sets themselves, and we have reached a point where we would like to abstract the concept, and fuzzy sets give you a way of doing it. How we do it will be covered in the next lecture, but now let's look at the need for fuzzy sets, how they were motivated from an application perspective. Now, this course is about approximate reasoning. So for reasoning, you need both knowledge and intelligence, as we have seen before. But let's ask ourselves a question, a different question perhaps. How does a human being think? Thinking is very much a part of reasoning. If you were to ask this question, without much effort, we would realize that we actually think in words, in terms of linguistic terms. Imagine you're sharing a room with your roommate and a visitor drops by, but unfortunately your roommate is not available at that time. And even before you could find out the name of the visitor, he leaves. Now when your roommate friend comes back to the room, you would like to describe this person to him. How would you describe him? Clearly, you would not have had the time or even the inclination to measure his height, so that you can tell your friend that he was 5 feet 7.5 inches in height and perhaps 63 kgs in weight. No, that's not how we describe somebody. Your description perhaps would be as he was tall, slim, and fashionably dressed perhaps. Now the question is, what is tall, what is slim, and how should one be dressed to be called fashionable? Now let's look at it. How tall should one be to be called tall? What should his height be? For instance, in India, you might say that somebody who is around 5 foot 9 inches can be considered tall. However, if you travel to the northern European countries, perhaps it's more or less an average height of anybody there. On the other hand, what you would consider as an average height for an Indian could well be somebody who is tall in Japan. So tall, as you see, is not only subjective but also contextual. Similar is the thing with being slim. And now coming to the last word, fashionably dressed. We'll know that this is a very time varying concept too. Not just subjective but contextual and time varying too. So all of this points out to this, that we perhaps think more qualitatively than quantitatively. Why is this important? Because we want to be able to capture knowledge. Knowledge comes from human beings, and if you want to capture them, you need a way of capturing this into a construct. A question might arise as to why we need to capture this knowledge. These days, we talk about machine learning. Perhaps a little bit of going back in history might give us a good perspective. There were times when automated systems were being used to support human decision makers. These so-called expert systems used probabilistic tools to arrive at a decision. However, people wanted machines to think like experts. If you want the machine to think like a human being, then it was important to understand how human beings thought. And as is clear, largely we think in terms of linguistic terms. So it was essential that we capture knowledge into a mathematical construct and give it a representation that is both appropriate and amenable for further processing. Now consider this question. When we measure something, we know that there are lots of possibilities for errors to creep in. There are different kinds of errors. All of us would have done some amount of experimentation, either in chemistry lab or in physics lab. There are these errors that are associated with the instrument itself, for instance, zero error. Then there are these errors that human beings introduce, like the parallax error. But then there are also these subjective errors. For instance, if you look at the picture on the left, if I were to ask you, is it a cat or a dog, each of us would have his own answer for it. Of course, it is clear it has to be either a dog or a cat. But looking at it, I think our subjectivity of how we are conditioned by the morphological features of a cat or a dog would lead us to answer accordingly. So, imprecision in measurement also necessitated the need for fuzziness. Many of these things we will see in more detail as the lecture series progresses. Finally, we talk about data analysis. Data normally are collected from processes which are typically nonlinear. However, it is very difficult to abstract the underlying model. Often, as engineers, you would readily understand that we resort to approximations, and often these approximations are with linear models. In the time fuzzy set theory was introduced, in the mid-60s, the controllers that were used or the models that were applicable or applied typically used differential equations or difference equations or integral equations. At that time, they felt a need for model-free estimators. And fuzzy inference systems were one way of building model-free estimators. A quick look at what we have seen in this lecture so far. From a theory perspective, we have seen that set boundaries can be vague. We need a mechanism to handle it, and there were clear theoretical and practical motivations for these. And if you were to be asked what is a fuzzy set, it can be thought of as capturing a concept. As we saw a few moments before, the representation that is given to the captured knowledge is very important, and if you want to capture it through this concept of fuzzy set, a useful, appropriate and an amenable representation is very, very important, and this is what we will see in the next lecture. However, before we close this lecture, allow me to flash at you a few seminal works. There have been quite a few. Perhaps my choice has been motivated by the content that we have covered in this lecture. This was the original paper of Lotfi-Zade, who is credited as the father of fuzzy set theory. His paper appeared in 1965 in the journal Information and Control, wherein he propounded his new theory of sets, the generalization of classical sets to fuzzy sets. Mind you, Professor Zade himself was an engineer, an electrical engineer from UC Berkeley, and he came to propound this concept of fuzzy sets from a purely practitioner's perspective. Soon enough, mathematicians also got interested in this, and within 2 years' time, there was a seminal paper outlining the theoretical underpinnings of fuzzy set theory in a very reputed mathematical journal by Gauguin. This is another paper of Zade himself, which deals in a more semantic way on what a fuzzy set is. This appeared maybe almost 15 years later, 1983. Allow me to flash at you just two more works which you could see as seminal. The first of them was almost 25 years after the first paper on fuzzy set theory by Zade, by Professor Frank Lavon, where he discusses fuzzy sets and vague environments, and this could probably resonate with you given the content that we have covered in this lecture. And finally, there's another very well-known, well-cited paper by Dubois and Prade, which deals with the different semantics that you could assign to fuzzy sets. We encourage you to have a look at these papers too. They are written very nicely and more in a story-like form, and we believe that these research papers are also at an accessible level to the audience of this course. So with this, we'll come to the end of this lecture. In the next lecture, as was flashed, we will look at finding a useful, appropriate, and an amenable representation for fuzzy sets. Thank you.